Welcome to the ALMEMO video tutorials on CSP technologies, data acquisition systems for performance testing. My name is Nicole Janot, and I have been working on CSP technologies at DLR for more than 6 years. My main fields of work are parabolic trough and component performance testing, as well as test evaluation and performance simulation. This unit covers the basics of data acquisition with respect to an application in performance testing. In particular, system requirements, guidelines, and typical procedures ensuring data quality will be discussed. Finally, an exemplary data acquisition system as well as a layout for loop performance testing will be introduced, and the contents of this unit will be summarized. The term data logging refers to the cyclical saving of measurement data to a database only. Though sometimes used synonymously, the term data acquisition system actually comprises the entire chain of conversion from the measurements to the results recorded. Thus, these systems consist of sensors, transmitters, and loggers. The sensors convert the physical measurements into analog electrical output signals. Some sensors, like particular inclinometers or Coriolis sensors, directly generate digital signals. For sensors typically used in performance testing, this is discussed in detail in Block 6, Unit 3, for example. An exemplary irradiance measurement is illustrated below with an electrical voltage induced by the irradiance on the sensor element. Transmitters perform the task of transforming electrical sensor output signals, thus conversion to 4 to 20 mA signals, analog to digital conversion, as well as signal amplification. In test facilities or test benches, this is typically performed by measurement boards. The resulting digital signals are then saved to a database by the logger or a corresponding function of the control software of the test facility. Devices called data loggers mostly combine the functions of transmitting and logging, and sensors complete the data acquisition system. Requirements for data logging and performance testing mainly result from general requirements in view of the desired data quality and needs of outdoor application. As part of the signal conversion, uncertainty characteristics of transmitters and loggers play an important role for data uncertainty. Therefore, in order to ensure good data quality, high precision and accuracy are to be aimed at. In particular, analog to digital conversion can be subject to major uncertainties. The resolution in time is chosen according to expected dynamics of the system under test. Typical values for logging intervals lie in the range of several seconds. In terms of the signals themselves, 4 to 20 mA signals are preferred for analog signals. Besides, the transmission lines should be kept as short as possible. Using digital signals often decreases the uncertainty of the measurement and increases its flexibility as it allows longer transmission lines. Furthermore, the protocol of digital signals often includes the sensor ID for easy identification of signals. This reduces the risk of signal mismatching. As the time serves as a reference base relating measurements during performance measurements, the synchronicity of records is one of the most important requirements for successful data analysis. If more than one recording device is involved, for example in the case of several loggers or logger and plant control, the internal clocks must be brought to agreement to provide a consistent time base for measurement data. Furthermore, for outdoor use under possibly harsh conditions, including high irradiation, dust, and precipitation, the equipment used must be robust. Mobile applications or adaptation to different measurement setups additionally require flexibility in terms of configurations and sensors. In order to facilitate setting up the sensors and loggers on site, it is advantageous if possible handling errors are reduced to a minimum. During the test, the operation of the equipment should be largely autonomic. Network operation options enabling central control and readout of the devices further increase the flexibility and ease of use. In the light of the particular requirements for mobile data acquisition, data loggers are preferred to standard electrical cabinets for mobile test configurations. A thorough documentation of sensor configurations, the test setup, and a full record of test operation is the key to successful data analysis and interpretation. In other words, it is relevant to check which signals were recorded where, using which sensors, and under what conditions. In this context, the following recommendations contribute towards ensuring good data quality. In order to prevent confusion, it is important to clearly identify signals and sensors, use the correct settings, and display their units. Adjusting the measurement range to the interval of expected readings maximizes the resolution of the signal. If correction and calibration factors like offsets or slope corrections are included directly in the data acquisition, the readings displayed during testing represent measurements and thus facilitate debugging, monitoring of test operation, and the identification of unexpected effects. Adapting display settings is another option to facilitate test monitoring. Cyclic averaging of readings is a means of reduction of noise and creation of a representative performance database at a selected time resolution. All sensor loggings and settings are to be logged in order to avoid accidentally changing them during testing. Although some of the measures mentioned could also be included at a later stage in data processing, these provisions are strongly recommended. As well as facilitating monitoring of testing, they ensure creating a complete database and help detecting problems during testing and avoiding mistakes during data analysis. A procedure for the installation and operation of data acquisition systems typically comprises the following steps. In preparation of a measurement, a functional test of the loggers is carried out, reviewing their internal clocks, their battery capacity or power supply, and available data storage capacity with respect to the requirements of the planned testing. Then, the signals of the previously mounted sensors are connected and their channels verified. This ensures the correct assignment of signal names and correction and calibration factors. Subsequently, the functioning of the sensors is verified and the plausibility of the readings checked. In case of later doubts and for documentation purposes, especially for temporary clamp-on installations, the sensors and their mounting situation as well as specification and nameplates should be photographed. In the next step, logging parameters such as the duration of the measurement and the logging frequency are set. At this point, the number of signals and the storage capacity required have to be checked, so that a storage overflow is prevented. The actual measurements with the start of the data logging. During testing, the system and logger operation is to be monitored and peculiarities noted. At the end of the test, data logging is stopped. Finally, the recorded data is made available for processing and analysis by readout. The practical implementation of requirements for performance testing is illustrated using the example of the ALMEMO system by Ahlborn. The loggers themselves include transmitters as measurement channels and are designed for autonomic outdoor use. They are relatively robust and contain internal batteries. The loggers use programmable plugs to be installed with the sensors, which store the domain, name, units of the signal, and conversion factors. This way, there is no risk of confusing parameters and signals, even though the measurement setup might vary. Furthermore, there is an option of building a network among different loggers. Using this feature, a number of loggers can be set up at different measurement points distributed in the field and operated by a central control for synchronization, checking, and data readout. For a utility-scale loop, for example, an exemplary data acquisition system would consist of 4 data loggers. One in the vicinity of the mobile meteor station, recording the direct normal, global horizontal, and diffuse horizontal irradiance, as well as the wind velocity, ambient temperature, and relative humidity of the air. One at the inlet, recording the HTF mass flow rate, the HTF inlet, and outlet temperature, as well as the tracking of the first and last collector. One in between the first and the second collector, and one at the crossover piping, each recording the HTF temperatures and tracking of the collectors. In the course of this unit, the requirements of data acquisition systems used for performance testing have been introduced. They comprise the synchronicity of all records, the unambiguous assignment of signals, device robustness, fail-safe operation, and low conversion and logging uncertainties. An exemplary implementation of a data acquisition system for loop performance testing has been illustrated. A number of best practice guidelines describing typical procedures and recommendations for data acquisition help assuring data quality. Furthermore, detailed records of system operation during testing periods are vital for the analysis and interpretation of test results at a later stage, especially if these are carried out by a different person than the one who did the testing. This brings us to the end of the unit on data acquisition systems for performance testing. Thank you very much for your attention.